Welcome to the third module of this short course on machine learning in communications. The theme for this module is theory-guided machine learning and unsupervised learning. We will be using these two ideas in a rigorous case study, which will be presented in lecture 6 later today. So in order to prepare for that lecture, what I did is I split this lecture 5 into 2 parts. The first part will introduce the general idea of theory-guided machine learning. And in the second part, I'm just going to introduce whatever we need for that lecture 6 from unsupervised learning. And then module 4 will be dedicated to unsupervised learning, where we will go through the details of expectation maximization and related ideas, and then develop another case study which will use those ideas. Right? So we will do that in module 4. Before we begin, I would like to thank my graduate student Kirtana Bogi, who helped me to put together this slide deck. So many of the ideas that I'm going to present are inspired from these two specific references that I'm showing here, both from IEEE transactions on knowledge and data engineering. We are also putting together something that is more specific to wireless systems, theory-guided machine learning for wireless. So if that materializes, we will also post that hopefully on archive soon. So please feel free to email in maybe a month or two if you would like to check the status or get a copy. Okay, so now when you think about the success of machine learning, right, that has been somewhat confined to some mainstream machine learning applications, things like natural language processing, computer vision, right? It has, of course, along the way transformed many commercial industries through these applications, such as retail and advertising, right? So I think it's natural to wonder why these specific applications benefited from machine learning, and the answer is quite straightforward. That is because of large volumes of training data, right? Think of all the images on the internet, this internet scale data that these applications can sort of learn from, right? So now it is easy to imagine why it has not had a similar impact on other scientific disciplines, right? The cost of data acquisition, for example, in many applications is prohibitive. Think of the equipment one would need to perform new propagation measurements in new bands, right? Think of, for example, propagation measurements in terahertz bands. So obtaining those measurements and making them available could be very costly. Further, this notion of machine learning being a black box solution may not really be acceptable to some communities, right? Even some people from communication information theory community may not be very comfortable with that notion, right? So the question is, what can we do about that, right? So let's quickly discuss a couple of shortcomings of machine learning and see where theory-guided ML, theory-guided machine learning fits. First of all, as I said before, we have just insufficient amount of data in most disciplines. And as we discussed in an earlier lecture, if you have insufficient training data, this will lead to overfitting, right? And once you have this overfitting, you're basically learning some spurious relationships from the training data, essentially learning noise, right? As I showed one picture in an earlier lecture. And because of overfitting, your models are not going to generalize well on the unseen data, even though they may work extremely well on the training data, right? And that's sort of the first deficiency, if you will, when you try to apply machine learning to some other disciplines. Now, second deficiency, which is of specific interest to theory-guided machine learning, is inconsistency of the models that you are training, right? First of all, trained models may not be interpretable, right? But even worse is when they do not comply with some basic physical laws which are governing the systems that we are trying to study, okay? For example, think about applications in physics or chemistry, right? There are basic physical laws that are governing those systems. And say you come up with a trained model and it turns out it's not really complying with those, maybe because of insufficient data, right? Now, that's not a very worthwhile thing to do. Right? If you want to think about a more abstract example in the setting that we've already introduced, think of our statistical model, y equals to fx plus some epsilon, right? F is the unknown mapping that we are trying to learn. Epsilon is just a zero mean random variable, as we have discussed before. Now, in general, we just don't know what this unknown mapping f is. But what if we know that this function f is, say, monotonic with respect to some very specific feature? Right? And then we find out that our model, the trained model, is not really complying with that. It's not really satisfying that condition, right? So we know that machine learning algorithm in that case is not doing what it is supposed to do, right? So the solution to these type of problems is to not ignore the domain knowledge, right? Think about communication information theory. There is vast domain knowledge in these areas. And it becomes even more important in the presence of limited data, as we will see in the case study of Grassmann clustering, which we'll do in lecture 6 today. Okay. So let's start going into some ideas of theory-guided machine learning, right? The general idea is to integrate some scientific knowledge to enhance the capabilities of ML, right? And I'll elaborate on this. As I said before, this is a bit of a high-level lecture, sort of introducing the ideas, but a more rigorous application will be presented in a later lecture. Now, this general idea is known by many names. If you come across physics-guided neural networks or theory-guided deep learning, theory-guided data science, they're all referring to essentially the same thing. Right now, the interesting thing about theory-guided machine learning is that it is combining two sort of complementary approaches. Think about a theory-based approach, right? When you develop a theory-based model, the models are consistent. So you might be selecting very limited features or inputs to that model, but then because those models are being created to describe the physical laws, they are consistent by design, but they are simple because we might be ignoring many other effects, right? On the other hand, you have this data-based approach where trained models are very complex by design, right? Because that's sort of what we are trying to do. We are trying to capture all the complexity. But along the way, they may not remain consistent because you're not telling them, right, explicitly what the underlying physical laws are. So you are hoping that those database models will learn those laws, but if your model complexity is too high, you might just need a prohibitive amount of training data for that to happen. So the objective then, right, once you start thinking in terms of this theory-guided machine learning idea, the objective now is threefold as opposed to twofold, which we usually have in machine learning. So the obvious targets in machine learning are, so your model should obviously be accurate, right? It should perform well. It should do what it is supposed to do. And the second is that you should not use a more complex model than you have to, right? And that's where the ideas of model simplicity or regularization or soft model selection and so on come into the picture. Now, in theory-guided ML, there is this third objective that gets added, which is physical consistency, right? We want our trained models to also comply with the physical laws. Right, so let's just take a very quick picture that I took from the first reference that I quoted on the first slide. So here we are just sort of comparing the use of scientific knowledge with the use of data, where each technique fits in. So on the x-axis, I have use of data going from low to high, from left to right. Similarly, on the y-axis, we have use of scientific knowledge, right? Think of use of theory, for example. Now, your data science models, which are lying here, they often do not use a lot of scientific knowledge, right? But the use of data is oftentimes very high, right? It's supposed to be high, of course, subject to the availability, because that's really what the data science models will be based on. On the other hand, if you look at theory-based models, right, they often use very little data, but use a high degree of scientific knowledge. Now, you might need little data. Now, think about wireless systems, right? The first step is to learn or is to model the propagation, right? So once you understand, and you do that through measurements. From measurements, you describe, say you come up with a propagation model, and then theory is based using or developed using that propagation model, right? So that approach is basically theory-based models using little data, but then a high amount of scientific knowledge. Now, this theory-guided data science models will lie somewhere here, where they are also using, so they are using both scientific knowledge and data, probably to varying degrees, depending upon where you lie here, okay? So things will be clear, a lot more clear actually from the example that we are going to do later today. But at this point, it's more about making sure we understand, right? So how to think about this theory-guided machine learning. Now, the workflow in theory-guided machine learning is as follows. This is a picture from the second reference, but a slight modification of a picture that I already showed you. I think it was the first or the second lecture where we were discussing supervised learning. Remember, our goal in supervised learning is to, so you have this unknown function, unknown mapping f, right, which is being observed through this training data, these training samples. We don't know what f is, right? So our only knowledge we have, right, in data science or a machine learning approach is to infer something about f through this data, through the training examples that are given to us. Then in the picture that I showed you earlier, right, this block was just a machine learning model, right, ML model that contained a machine learning algorithm and the choice of a hypothesis class. So in this paper, they are going into some more discussion on feature engineering. That's why you see a few more blocks here, but that's not really required for what we want to do. Now, in theory-guided machine learning, right, in addition to observing f through data, right, this unknown function through data, we might also have some prior knowledge about this function f that we are interested in learning. So we integrate that into the machine learning model, and then we get the final hypothesis, right? We will see how we can integrate that. I mean, that's sort of going to be the topic of the rest of the slides. Now, let's first discuss, right, how could this prior knowledge be represented, right? In what forms could it come? Obviously, the answer is it is highly context specific, right? Really depends on what you are trying to study. The common forms could be algebraic equations, right? You could have logic equations if there is some type of temporal evolution in the system. Or even spatial evolution of the system. You could have differential equations. You could have probabilistic relations. You could have invariances in the sense that your solutions might be invariant to certain mathematical operations. And that is basically today's case study on Grassmann clustering in lecture 6, where we are really going to exploit this invariance property we will have in our solution. Now, this can be integrated in the learning process, right? Whatever form the knowledge might come, it could be integrated in the learning process in multiple ways. It could impact your training data, as we'll discuss. It could impact the choice of your hypothesis class. We're going to discuss that a little bit now and in a lot more detail in lecture 6. It could even impact the choice of your, or even choice or design of your learning algorithm. Right, and this will also be partly covered in lecture 6. And by the way, so once you integrate knowledge, right? So it's not that it's only doing one of these three, or these are not even exhaustive. One of these things, it could impact multiple things, as you see here in the case study, sort of reference to the case study. For example, if your prior knowledge shrinks your hypothesis class, right? It tells you that certain functions you should not even care about, right? In your hypothesis class, you should limit your search to specific functions. That means that you probably don't need a very complicated learning algorithm. So that could also impact your choice of learning algorithm, which is sort of what happens in that case study as well. Let's look at this knowledge integration part one by one very quickly. So you could impact your prior knowledge could impact your training data. This could be, for example, by augmenting training data, right? You could have, for example, training data obtained from measurements. Then you might be able to use your theory knowledge to augment that training data, either adding more samples that come from theory or adding more features that come from theory, right? So there could be some type of augmentation in training data that could be theory guided. Now, the question I have for you here is, can you think of such an example from communications, right? And since we are going to have a live session in the evening, I would really love to hear your thoughts. So let's have a discussion regarding this in the live session. The second way in which you could integrate your knowledge is in the hypothesis set or hypothesis class itself, right? Recall that a smaller hypothesis set is desirable to avoid overfitting, right? For example, if you can live with, say, a linear model, right? That is better than using, say, a very complicated model for which you might need a lot more data and still you might have problems training that, right? So smaller hypothesis classes are usually desirable. This might be in particular true for inference problems, right? Where you want to have some functional forms and things of that sort. Now, prior knowledge can help with this constraining of hypothesis classes through the choice of appropriate loss function or model architecture, right? So let's see, what do I mean by these two things? Let's first look at the model architecture. What I mean by that is, once you know, right, what you are trying to do, once you have some understanding of the problem setup, you could actually choose, for example, the architecture of your neural network based on that. And there are already examples from the wireless communication literature where something like this is done. For example, if you're interested, check this deep MIMO detection paper, where the neural network architecture is actually influenced by the MIMO detection process. Okay. Now, something that's a little bit, I would say, a bit more general is in incorporating this knowledge in the loss function that can be treated as theory-guided regularization. Okay. For instance, what you could do is, say you have a certain physical law, you want your model to be consistent with that physical law. You could put a large penalty, right, whenever that law is violated. And that large penalty term could come in the loss function, right? And as we have discussed before, these type of additional terms can be thought of regularization, right? Depending upon in what context are those terms added. We have seen those terms in the context of priors, right? Which are also trying to help you search in sort of the right direction by giving some prior belief in a Bayesian setting. So here, this is theory-guided regularization, because what you are trying to tell your machine learning model is that whenever there is a large penalty loss, you are trying to push your learning algorithm away from a certain type of functions, which will violate that whatever physical constraint you have in mind, right? So as I said before as well, in lecture 6, we will see how this invariance property of the solution, we'll discuss that in more detail, will help in restricting our hypothesis set, right? And we'll also see that how this further helps in coming up with a very simple learning algorithm, right? Rather than directly going to, for example, deep learning, you could do something far more simpler and still get a pretty reasonable solution. Okay, so one of the last things, right, where knowledge how knowledge could be integrated is in the learning algorithm itself. There are many ways in which knowledge could impact learning algorithm. starting from choice of learning algorithm, right? What type of learning algorithm should I use? Do I really need deep learning? Do I really need a neural network, or is something like k-means enough, right? We will have this very brief discussion in the case study again. It could impact initialization, right? People who have worked with deep learning, I'm sure would agree that we really need to avoid bad initializations, right? Because of the problem being non-convex, you might be stuck in bad local optima. So one thing you could do is to pre-train your model on physically consistent data. Now, this data could just be simulated data, and then you use that pre-trained model as an initialization, and then fine-tune that model using real measurements, right? That's how prior knowledge could come in initialization process. You could use theory-guided priors. Now, this is pretty sort of, I think, irrespective of what domain you work on, you can sort of make sense of this bullet point quite easily. So from theory, you can have a certain belief about your solution, right? And you can put that belief into a prior, and then use a Bayesian setup to develop a better learning model. For example, if you are estimating a certain parameter, right, from using, say, deep learning, you could put a prior on that parameter that comes from theory, right? That's sort of your prior belief. And this is, in this case, you are not really putting a very strict constraint based on the physical law. You are actually putting a soft constraint, right? You could have a very hard constraint, you could have a soft constraint. So this is more of a soft constraint idea. Then you could have constraint optimization, right? Where some constraints that you might have will restrict the space of feasible model parameters. So these are all sort of related in one way or another. Okay. So this is my second last slide. So final note, you could also have something called hybrid models, right? We can think of hybrid combinations where you have some parts of the problem which are handled by theory-based models. You could have other parts of the problem which are handled by data-based models, right? So this is what this theory-guided machine learning community calls sort of hybrid models. And interestingly, we have already come across one example. Since I had not introduced this idea of theory-guided ML in the first lecture, or first day rather, I did not bring this up then. But the idea of determinantal learning for subset selection that we studied on day one actually fits very nicely in this category, right? Remember, what did we do? We had this, let me just go to the case study and not to the general idea of determinantal learning, which we of course discussed in a lot of detail. So please check that lecture again if you're interested. But in the case study, what did we do? We had some wireless links, right? And we wanted to schedule a subset of those links in order to maximize the network performance, right? The network performance in that very specific case study was just some rate, right? And we knew that, whatever reasonable algorithm you use, optimization algorithm you use, you're not going to schedule 2 points or 2 links which are very close to each other, right? Because of the very high interference. Using this idea then, or inspired by this idea, and I would say this is sort of theory-based knowledge, right? This is coming from the domain knowledge. We then said that let's select a probabilistic model that puts certain probability distribution on the selection of these links from my base set. And the selection is such that if you select one link, then selection of its very close link is negatively correlated. And that was a determinantal point process, right? That again comes from, I would say, sort of domain knowledge. And then we learned its parameters using machine learning, right? That was sort of a nice hybrid solution. And we also showed that even so, while this subset selection problem is NP hard, there are heuristics, but even the heuristics don't work if you have moderate to large sizes of the network. But using this hybrid approach that we developed, you could come up with schedules for even extremely large networks, right? Now, I should make a note here that this general approach of selecting a model, right, a probabilistic model, for example, and then learning its parameters is really the foundation, right? It's very, very popular. This theme has stayed throughout, right, with us since we started this short course. But it starts also coming under the purview of theory-guided machine learning when this model that we have selected is inspired by theory, right? It's inspired by some type of prior knowledge that you already have. All right. So with that, we are ready to conclude this extremely short, quick introduction to theory-guided machine learning. A few very quick points, right? In all scientific disciplines, we have vast prior knowledge that must not be ignored, right? Just because deep learning worked very well in some domain doesn't necessarily mean that we have the same conditions, right, in every scientific disciplines to have that type of impact. So we should make sure that whatever knowledge we have is sort of supplementing or complementing the machine learning solutions. Now, theory-guided machine learning is highly context specific. This will be clear from the case study today, right? It really depends on the type of knowledge, in what way is it represented, how to then use that best in the machine learning model. You may have to come up with innovative techniques to do that. One could now enforce these physical consistency constraints, right, which are really at the heart of theory-guided machine learning. You could do this strictly, right, by designing model architectures or specifying certain constraints, or you could do it softly through choosing appropriate priors or regularization terms, right? As I remarked early on, this is an area which I'm sort of thinking about right now. I would really love to hear your thoughts on problems in communications that can benefit from theory-guided ML. We can have a discussion in the live session, but if you have any thoughts, any suggestions, any ideas, please feel free to send me an email. My email address is given here. All right, so thank you very much, and I will see you in a little bit in the second part of this lecture where we will give a very brief introduction to unsupervised learning.